the last presentation in this session. It's a scenario generalization of data-driven imitation models in crowd simulation. So one more take them in crowds. Okay, so I think the authors of the paper are not here, right? So he's going to be doing this presentation.
So this presentation will be very quick. Yeah, so today I'm Rohit, by the way, and I'm doing my PhD from ETH today. And the authors unfortunately could not make it to the conference, so they asked me to present it on their behalf. It was short notice, so I tried to do my best. And we will be talking about the scenario generalization of data-driven imitation model in crowd simulation. So mostly, for the clarity of the presentation, I'll read from the notes, so excuse me for that. So let's begin. So we have seen a lot of presentation on crowd simulation. So this is one more. So basically what we are seeing is, let's start the video. And what we are seeing here is that the agents, there are 6 different environmental layout and complexity, and the agents have their own start and end position. So what we have to do or aim for is that every agent decides on their own autonomously. They do not have a centralized brain which tells them, okay, this is your next velocity and this is the next time step which you should take. So this is the goal which an imitation model should have. Okay, so the motivation here is, the problem is that we want to learn from a data a model of crowd motion which can be generalized in any arbitrary environment. So this problem is not simple, and to do that we make 2 relaxations. The first one is we provide a trajectory which is based on an expert trajectory. I'll come to that in the future slides. And the second relaxation which we do is that we learn a model from the demonstrated expert trajectories such that the learned model could imitate the decision making by the trajectories from an expert. However, this particular solution is not a simple solution to solve. Scenario generalization is not easy. By scenario, what do we mean? We mean that we train a particular model in a different environment with a different set of agents, number of agents, their start and end positions, and then we test it out in a completely different new scenarios. So it is not a simple problem. So our aim here is to study the impact of training paradigm and training data. So I'll repeat here, I'll stress it here. So the goal of this particular work is to understand the training paradigm and the training data which should be used for scenario generalization. Okay, so this is a rough illustration of how an imitation model should look like. So on the left we have an expert trajectory. So there are obstacles, the agents are there with the circle, and the blue rectangular thing is an obstacle here. So we have an expert trajectory, we record that. F of ST is the imitation model, F is the imitation model, and ST is the observation at each time step. The observation here are the environment layout and the start and end position. And the goal of this imitation model is that it churns out velocity, which is represented by AT here, of each agent. So this is, and that's how we get a new scenario of the imitation trajectories. It can be further abstracted into this kind of scenario. So this black box can be our imitation model. And for during the training scenarios, we can give them 2 parallel inputs, which are environmental configurations and the initials of the agent start and end positions. And during training, we also give them the trajectory performed by an expert model. And during the testing part, will be only given the first parameter, the environmental, and the initial destination, and the output is missing. And the goal of the imitation model is to churn out this particular trajectory. Okay, so this problem of scenario generalization and regular generalization have been studied quite a lot. But in our opinion, when we were probably solving this problem, we understood that scenario generalization differ from regular generalization in a subtle way, but in a few different ways. So first of them, there are 3 different ways they differ. The first will be that in regular generalization, the model has full information of the environment. They have every obstacles and start and end position of every agent. But in the scenario generalization, the information is only for the neighborhood. Like every agent is autonomous and it has its own knowledge and or maybe a knowledge of the neighborhood, but nothing more than that. So it differs in that way. The second way it differs is for the regular generalization, the test samples are generally isolated. I mean, the previous test sample do not get influenced by or the next test sample do not get influenced by the previous sample. But in the sequential and the scenario generalization, each agent's time step or the next step is somehow get affected by the previous agents. And finally, they differ in the, in regular generalization case, they are isolated in state action pair, but in the measurement of scenario generalization, the overall generated trajectories are affected by multiple metrics and some of them might be mutually balanced. Okay, so this is a brief literature on the cloud simulation, which we will not go because everyone is expert here but me. Generally it is categorized into three categories: the rule-based, behavior cloning, and reinforcement learning. So the rule-based methods are generally the social force model and the Orca model. They are data independent. They don't depend on data. They have their own set of rules and the agent follows that. Behavior cloning and reinforcement learning are the two. Remember I mentioned the training paradigm. So this will be the two training paradigm which we will be using, and rule-based will be our expert model. That will be used to generate trajectories. So the main goal of this particular work is to understand the training paradigm and the training data that should be used so that scenario generalization gets benefited the most. So that is our goal here. So this will be the problem formulation for behavior cloning. So the idea behind behavior cloning paradigm is to minimize the reactive loss, which we can see by the formulation in equation 1. The reduction occurs when the cost function C, ST and AT is predefined differentiable training loss function with discount factor being the constant one, and the dynamic depends only on the data distribution independent from the current state action pair. In this view, training a model in behavior cloning paradigm is something similar to having a supervised regressor or fitting a neural network regressor with the cost function. Let's discuss the problem formulation for reinforcement learning. So the objective of reinforcement learning is to maximize the accumulated reward via inverse RL. Based on Ho's work, which shows that RL and both inverse RL solve the primal and the dual problem of occupancy measure matching, with optimal solution forming a saddle point. That means at any two steps, the inverse RL and RL is equivalent to a one-step formalization which we highlight in equation 3. And that is, the psi here is represented as occupancy measure of an imitator. And Ho's work further shows that there exists a specific psi which that is the equation 3 can be further reduced to an adversarial form with the model imitator serving as the generator of model trajectories, and the reward function serves as a discriminator. So this particular line here is the reward function which tries to discriminate between the orange shaped cloud and the green shaped cloud. The orange one is from the imitator model and the green one is the expert trajectories. When that particular cloud overlaps the expert trajectories, what we notice is that our imitator model is generally presenting or churning out the trajectories which are similar or as good as the expert model. So that is the goal. Okay, so we have two training paradigm, behavior cloning and reinforcement learning. So now let's set up our data domain. So we will use three different data domains. The first one is the exocentric standard domain, which we abbreviate as X. So there are 6 different scenarios. These environmental scenarios are generally benchmarked and used in most of the cloud simulation. So the key feature for this particular data is So the key feature for this particular database is that it is complex and it is crowded scenario and includes 6 different variation of the environment. The second data domain which we use is egocentric, random, and which we refer it abbreviated by R. So the thing which we need to notice here is that there is no obstacle. So agent obstacle collision is not recorded in this particular data domain. And the third domain is the egocentric representation scenario. This is the large number of sampling of small scale samples, which generally includes both agent and agent obstacle domains. So in this we have like 4,000 scenarios for training and 100 scenarios for testing. So this is our data domain, 3 different data domains, and now we will come to the metrics. What metrics should be used to measure the output of the imitation time? So there are 3 different metrics which we use. The one is the dynamic time warping, agent-agent collision, and agent-obstacle collision. Dynamic time warping measures the deviation between the trajectories of an expert model and an imitator model. Agent-agent collision and agent-obstacle counts the number of collisions which is happening. We also apply the method of bidirectional experiment, which means that we test it on the data domain G and R, evaluate on X, or we train it on X and R and evaluate on G. One thing to note here is that the reinforcement learning, which is represented by RL, is not trained on the data set R, because reinforcement learning needs a complete set of information which is not provided in the data domain R. It is the snapshot, the random snapshot. So here, in short, we see a state representation for one agent. The thing which you see in blue is the field of view, which an agent can see, and the white are the exclusion either by the obstacles or from other agents. So now coming to the results. So the results is quite straightforward, which is displayed on the left hand side of the image. To read this particular image, we need to just keep in mind the smaller the better. So something which is 1.2 for the DTW scale is better than the 2.6. So here we experiment with the both reinforcement and behavior cloning. And what do we see here? We see here that for DTW, for the measure DTW, behavior cloning, when it is trained on G and outperforms the reinforcement learning for both AA and DTW. But for AO, which you see here, is 1.3. 1.3, the blue color thing measures RLA. So RLA outperforms the behavior cloning. And this is due to an outlier. And then we will come to that outlier in a video which we will show you in a couple of slides. So for time being, what we notice here is that given same training domain G, BCA is better than reinforcement learning, which we after excluding the outlier. Moreover, given the same paradigm BCA, the data domain G is better than R in agent and agent obstacle when applied to X. We run the experiment on the second data domain G, and it's the same way to see the smaller the better. And we see here that for DTW, AA, and AO, behavior cloning method, which is a simple method, outperforms the reinforcement learning in each data domain and scenario cases. So what do we observe here? It's similar, given the training domain X, BCA is better than reinforcement learning, and R is better than X in both AA and agent obstacle when applied to G. So we took it one step further and then we applied it into the real world domain. So this particular data set is, I think, from a standard from Stanford data trajectory, and it is a video serverless data of a real human being walking at a train station. And it is applied in all 5 scenarios. So the 6th scenario is missing because we are not training reinforcement on the R data domain because it's incomplete. So what do we see here? Visually, we can see that behavior cloning on G and behavior cloning on R fits the data much better and properly compared to all the reinforcement learning method. So very quickly, we will see a video. So this video basically highlights the outlier and the previous images. So here we will see 2 videos. So in this, behavior cloning is being trained on X and tested on G. All the light lighting effect which you see, the blinks are the collisions. So these are the collision which is happening, and by default blues are the obstacles and circles are the edge of the black circles. So this was for PCA trained on X, test on G. Now we will see behavior cloning just after this being trained on R, and we are testing it on G. So again the same, the blinking part is the collision which is happening. So we do measure it, but first forward it. So we complete the simulation. So what do we observe here? So we observe on the left hand side, we see on the data domain X, there are certain collisions which is being happening and are marked with red. And the same collision is not happening in PCA when it is trained on database R and test on G. And the conclusion why this happens is because the training domain R, which has more agent and agent collision. Remember, R did not have any obstacles, so it did not have agent obstacle collision. It had more agent collision, so that's why it was better. In the second video, we will see why we saw the outlier. So when we train using the reinforcement learning, we can see these kind of weird effects. So on the left hand side, on your left hand side, you see a lot of agents, they are unable to cross it, and this is because the conservative nature of reinforcement learning. So agents are trying to avoid each other and unable to enter the hallway, and that's why for agent-agent collision, they have the best performance because they're not even entering, so how will they collide? So now we can just see for every different environmental scenarios how the BCA outperforms parallel. Like this is the concentric circle. Next we will see a hallway. So this is like a one-way corridor, so visually we can easily understand that BCA is outperforming parallel. Then it will be a crossroad, I guess. Yeah. So finally, so what do we learn from all this? So the conclusion here is that simple training paradigm is better than the complex one. And moreover, the training data with diverse agent obstacle and agent-agent interactions are better for reducing the collision and models applied in new scenarios. And when it comes to real world, model trained on random and representative scenarios generalizes to new unseen situations observed in real human crowds. Thank you. I can hardly answer any question, but I'll try.
Who wants to start with the questions?
Do you have any idea how many iterations are performed for the reinforcement learning?
No.
Or
I can
because of the
trajectories. I can get back to you after asking that.
okay. I'm sorry.
So one question which I think people should ask is why? Why the simple scenario is better than the complex reinforcement learning? So if anyone has that question, please ask and I can answer that.
Okay, let's assume somebody asked that question. Let's see if you have an answer.
Okay, so the answer I think is based on this. So what we see, I think the authors gave me this question because they thought that this is an important one to answer. So according to them and the formulation, this is the complex reinforcement learning formulation, the PS-S A, when we train the complex scenario, it inherently implicitly takes the environment and the agent obstacles location in the model when it trains. So when we change the scenario, these implicit information which is stored in the model in a completely different scenario starts giving an adverse effect. So in simple words, when you train anything in using complex environment, complex like reinforcement learning method, the environment or the scenarios get implicitly embedded in the model, and that's why this happens. Okay.
I ask a simple question. the state representation that they're using, it's like separate.
Yeah.
Typically with agents, you try to assume there's a perception region. You don't typically assume agents are aware of what's behind them. Do you know why they have chosen that center?
No, but I totally agree. They should not have
Okay.
placed it. So I don't know why.
So did you mention why they chose Gale instead of MGale? Because the paper, I just read the paper. They for the imitation learning part, they used the generative adversarial imitation learning framework. But from that same group, there was a multi-agent version of it later, so which actually considered a lot of the agent, interaction, including collisions. So I wonder if they mentioned why they chose Gale instead of MGale. No.
I didn't ask them. Sorry to disappoint you guys.
So I think it's time to go for lunch and email the questions to the auditors.
Thank you so much.
Thanks for the presentation.